All right, this is physics lesson 4.5. We're going to learn about the difference between mass and weight today. We need to quickly review what mass is. In physics, we define mass as a measure of an object's inertia, which is great, but unfortunately it doesn't help us a whole lot understanding the difference between mass and weight. So we're going to use the chemistry definition, which is this. Mass is a measure of how much matter makes up an object. Okay? So notice, an object's mass is a property of the object itself. In other words, if I give you an orange and we measure the mass of that orange, basically what we're doing is we're counting particles, right? The more particles it has, the more protons, electrons, and neutrons that it's made up of, the more matter it has, and therefore the more mass it's going to have. And no matter where we take that orange, the mass is always going to stay the same, right? So if I take my orange to the moon or to Jupiter or to the farthest reaches of outer space, it's still made up of the same number of particles, so the mass always stays the same. All right? For this class, mass is always, whoa, it's not what I was trying to do. Let's try that again. For this class, mass is always going to be measured in kilograms, okay? I guess you could use grams, but that's pretty much it for the purposes of this class. Okay, kilograms is mass. Okay, so weight. Weight is often confused with mass, but they're really very different things. So here's the definition of weight. The definition of weight is the force of gravity acting on an object. And for that reason, the symbol for weight is not actually a capital letter W, but instead it's capital F lowercase g, which stands for force of gravity. All right, I cannot possibly stress this enough because people forget this every year. If I ask you the definition of weight, it's force of gravity. Weight and force of gravity are synonymous. Okay? When we talk about weight, we're talking about the amount of force that the Earth's gravitational pull has pulling an object down towards the center of the Earth. Okay? So you need, like, put that in your head, that weight and force of gravity mean exactly the same thing. Okay? So the reason that we have weight on Earth is because the Earth has a gravitational pull, right? This pulls us and all objects on the Earth towards the Earth's center. And this is why your feet get tired if you stand all day, because because your body is constantly being pulled down. All right? If you go to the moon, there's less gravity on the moon, so you don't weigh as much. And as a result, if you stood all day on the moon, your feet wouldn't get quite as tired. All right? In the deepest reaches of outer space, there's no gravity, so you're what's called weightless. If you imagine standing on a plank in outer space, your feet don't get tired because there's nothing pulling your feet down towards that plank of wood. Okay? Now, because weight is a force, weight is always going to be measured in newtons in the metric system, or pounds if you don't use metric. All right? Obviously, we're going to be using the metric system, so we're going to use newtons. All right, so at this point, what you should be thinking is, okay, so mass is always measured in kilograms, and weight in this class is always measured in newtons. Mass is m, weight is, what's the definition? Oh, force of gravity. Okay, so there we go. So here's where this gets a little bit confusing. The reason that mass and weight are so often confused is that because for a given location, in other words, Earth, for example, they're proportional. On Earth, if Roy has twice as much mass as Sally, he also has twice as much weight as Sally. Okay? So on Earth, for example, if Roy's mass is 90 kilograms and Sally's mass is 45 kilograms, what's going to end up happening is, we're going to learn why in a minute, it turns out that Roy's weight is 900 newtons, which is about the same as 198 pounds, and her weight is 450 newtons, about 99 pounds. So the idea is, look, Roy has twice as much mass, he also has twice as much weight. Okay? So they're very, very closely related. More mass generally equates to more weight. Okay? If you go to Europe and you ask somebody, hey, how much do you weigh? They're going to give you their weight in kilograms, which is wrong. Okay, and usually I tend to side with Europe on stuff like this because they use the metric system. But in this case, they're using the metric system wrong. All right. To be proper, if you in America, if you say, how much do you weigh? You know, if you went to Roy and said, how much do you weigh? Roy would tell you that he weighs 198 pounds, which is correct. If you went to Europe and you said, how much do you weigh? He would say 90 kilograms, which is incorrect. That is not his weight, that's his mass. To correctly give you his weight in Europe, he should say 900 newtons. And for whatever reason, Europeans do not use newtons. All right, so it ends up being kind of a non-issue because, like I say, they're proportional, right? If you lose weight, you're also losing mass, right? So, okay, I don't know if that rant made any sense. Ultimately, what you need to know is that mass is measured in kilograms and weight is measured in newtons. I think if you know that, you're in good shape. To continue this example here, if Roy and Sally both go to the moon, notice they both still have the same mass, right? Roy's mass on the moon is still 90 kilograms, and Sally's mass on the moon is still 45 kilograms. But they both weigh less, about a sixth as much, because there's less gravity on the moon, okay? And then in outer space, where there's no gravity at all, in outer space, they still have mass, the same mass they had on Earth and on the moon, but no weight, right? Because there's no gravity in outer space, okay? So there you go. So now, what's the connection between weight and mass? Well, in chemistry, you probably learned that a pound is 454 grams. Unfortunately, that's only true on the Earth. All right. So in physics, we use a more solidified, I guess, relationship between mass and weight, and it's very similar to Newton's second law. And here's what it says. It says to calculate the weight of an object, you take the mass of the object and multiply it by the acceleration of gravity. Here that is in symbols. Weight equals mass times acceleration of gravity. And remember, on Earth, the acceleration of gravity is negative 10 meters a second squared. Okay? On the moon, it's negative 1.66 meters a second squared. In outer space, it's 0. Okay? So, I think let's apply that to a problem. All right? So here we go. It says a dog has a mass of 30 kilograms on the Earth. So somewhere you should write down, oh, his mass is 30 kilograms. Okay? Here's two other facts. The moon's acceleration of gravity is negative 1.6 meters a second squared. That's only one other fact. I changed that. Okay, here's one other fact. So what's the dog's mass going to be on the moon? Remember, mass is a measure of matter. Does the dog's mass change when he goes to the moon? No. So it's still going to be 30 kilograms. All right. What about in outer space where there's no gravity? Well, even though there's no gravity, the dog still has mass. He still has the same amount of matter that he had on the moon. So his mass is still going to be 30 kilograms. All right. Now, what about weight? When I say find the weight, I'm asking you to find the force of gravity. So force of gravity is mass times acceleration of gravity. So the dog's mass is 30 kilograms. On Earth, the acceleration of gravity is negative 10 meters a second squared. So you multiply and you get negative 300 newtons. So the dog weighs negative 300 newtons. And the negative is just telling you that it's down. Gravity pulls stuff down. Gravity's pulling. If this is my dog, that's a dog, then gravity is pulling him down with a force of 300 newtons. Okay? Now, it's not unusual to just say the dog weighs 300 newtons, and you just sort of understand that it's negative. So occasionally in a problem, I might say, a dog weighs 300 newtons, and it's up to you to determine that it's negative. Okay? Now, on the moon, the dog is going to weigh less, right? He's still 30 kilograms, but the acceleration of gravity on the moon is negative 1.66 meters per second squared. So that gives us negative 50 newtons. He weighs less on the moon because there's less gravity. Okay. Finally, in outer space where there's no gravity, his weight is 0 because there is no gravity in outer space. Okay? So there you go. One last example. We can go backwards too. If you have a cow that weighs 5,000 newtons, I'm telling you that the force of gravity on the cow is 5,000 newtons. Negative, because gravity pulls down. So if Fg equals mag, some algebra shows us this. So the force of gravity on our cow, the weight of the cow is negative 5,000 newtons. The acceleration of gravity on Earth is negative 10 meters per second squared. So we've got a cow that weighs, or that has a mass of 500 kilograms. There you go. There's the mass of your cow. Please notice you cannot have a negative mass ever, ever, ever. All right, I'm going to stop there. I came so close to hitting 10 minutes. Have a good day.